ground wire is required to be run in metal conduit when the conduit is not considered a ground in the following situations. Firstly, when the conduit is not continuous. If the conduit is not continuous, such as when it is interrupted by a junction box or other fitting, a ground wire must be run through the conduit to maintain the electrical continuity of the ground path. Secondly, when the conduit is not properly bonded. If the conduit is not properly bonded to the electrical panel or other grounding electrode, a ground wire must be run through the conduit to establish a grounding path. Thirdly, when the conduit is installed in a corrosive environment. If the conduit is installed in a corrosive environment, such as a damp basement or outdoors, a ground wire must be run through the conduit to protect the conduit from corrosion. Fourthly, when the conduit is used to protect a grounding conductor. If the conduit is used to protect a grounding conductor, such as a bare copper wire, a ground wire must be run through the conduit to ensure that the grounding conductor is properly protected from damage. Let's delve into each of these scenarios in more detail. Considering the first scenario, a non-continuous conduit system, the integrity of the grounding path is paramount for electrical safety. Metal conduit, when properly installed and connected, can serve as an equipment grounding conductor. This means it can provide a low impedance path for fault current to return to the source, facilitating the quick operation of overcurrent protective devices like circuit breakers or fuses. However, this ability relies heavily on the continuous electrical connection throughout the entire conduit run. Think of it as a chain. If one link is broken, the entire chain's ability to conduct is compromised. When a conduit run is interrupted by a junction box, a coupling, or any other fitting that doesn't ensure electrical continuity, the grounding path is broken. This is where a supplemental ground wire, also known as an equipment grounding conductor, becomes essential. This wire bypasses the discontinuity, providing a reliable grounding path from the electrical equipment back to the grounding electrode system. The size of this ground wire must be appropriate for the circuit's overcurrent protection, as specified in the National Electrical Code, often referred to as the NEC, in Table 250.122. This table dictates the minimum size of the equipment grounding conductor based on the rating of the overcurrent device protecting the circuit. For example, a 20 amp circuit may require a 12 American wire gauge, often referred to as AWG, copper ground wire, while a larger circuit, such as a 60 amp circuit, would require a larger gauge wire like a 10 AWG copper ground wire. The importance of maintaining a continuous ground path cannot be overstated. In the event of a ground fault, where a live conductor comes into contact with a metal enclosure or other conductive part, the fault current needs a low impedance path to return to the source. This high current flow causes the overcurrent device to trip, quickly de-energizing the circuit and preventing electrical shock hazards or equipment damage. Without a continuous ground path, the fault current may find other paths to ground, potentially through a person touching the faulty equipment, leading to a dangerous electrical shock. Secondly, let's examine the scenario where the conduit is not properly bonded. Bonding refers to the permanent joining of metallic parts to form an electrically conductive path that ensures electrical continuity and the capacity to safely conduct any fault current likely to be imposed on it. Proper bonding is crucial for the metal conduit to effectively function as an equipment grounding conductor. If the conduit is not properly bonded to the electrical panel or the grounding electrode system, its ability to provide a low impedance ground fault path is significantly reduced. Several factors can contribute to improper bonding. Loose connections, corroded fittings, or the use of incompatible materials can all compromise the integrity of the bond. For example, if galvanized steel conduit is connected to an aluminum junction box without using a suitable anti-oxidation compound, corrosion can occur at the joint, increasing the resistance of the connection and hindering its ability to conduct fault current. To ensure proper bonding, several techniques are employed. Conduit fittings are designed to provide a tight, secure connection that maintains electrical continuity. Bonding jumpers, which are short lengths of wire used to connect metallic parts, are often used to bypass questionable connections or to bond equipment enclosures to the conduit system. The NEC specifies requirements for bonding in Article 250. These requirements cover the methods of bonding, the types of bonding jumpers allowed, and the sizing of bonding conductors. For instance, the NEC mandates that all metal raceways, cable trays, and other metal enclosures containing service conductors must be bonded to the grounding electrode system. This ensures that any fault current on the service conductors has a direct path to ground. When the conduit system is not properly bonded, a ground wire inside the conduit provides a dedicated low-impedance path for fault current, ensuring the reliable operation of overcurrent protective devices. This ground wire acts as a redundant grounding path, mitigating the risk of a high-impedance fault that could lead to a dangerous voltage in the metal conduit. Consider a scenario where a metal conduit run is connected to a junction box using lock nuts and bushings. If the lock nuts are not tightened properly, or if the surfaces are corroded, the connection between the conduit and the junction box may not be electrically continuous. In this case, a bonding jumper would be installed between the conduit and the junction box to ensure a reliable grounding path. Moving on to the third scenario, where the conduit is installed in a corrosive environment. Corrosive environments pose a significant threat to the integrity of metal conduit systems. Exposure to moisture, chemicals, or other corrosive agents can degrade the metal, leading to rust, pitting, and eventual failure. This corrosion can compromise the conduit's ability to function as an effective equipment grounding conductor. In highly corrosive environments such as chemical plants, wastewater treatment facilities, or coastal areas exposed to salt spray, the rate of corrosion can be accelerated. Even in less extreme environments, such as damp basements or underground installations, corrosion can gradually weaken the conduit over time. When metal conduit is installed in a corrosive environment, the NEC typically requires the use of corrosion-resistant materials or coatings. For example, rigid polyvinyl chloride, often referred to as rigid PVC, conduit is often used in underground applications where it is exposed to moisture and soil chemicals. Similarly, galvanized steel conduit can be coated with a layer of zinc to provide corrosion protection. However, even with these protective measures, the risk of corrosion remains. The ground wire installed inside the conduit provides a redundant grounding path that is not susceptible to corrosion in the same way as the conduit itself. This ground wire ensures that a reliable grounding path is maintained even if the conduit corrodes over time. The NEC addresses the issue of corrosion in Article 300.6, which requires that electrical equipment and wiring be protected from corrosion. This section mandates the use of materials and methods suitable for the environment in which the equipment is installed. In addition to using corrosion-resistant materials, regular inspections and maintenance are essential to identify and address any signs of corrosion before they become a safety hazard. Finally, let's consider the scenario where the conduit is used to protect a grounding conductor. In some cases, a bare or insulated grounding conductor may be run through a metal conduit for physical protection. This is often done in situations where the grounding conductor is exposed to mechanical damage or abrasion. While the conduit provides physical protection, it is essential to ensure that the grounding conductor is properly protected from electrical faults. If a fault occurs within the conduit itself could become energized, potentially creating a shock hazard. To prevent this, a ground wire is run inside the conduit along with the grounding conductor. This ground wire provides a low impedance path for fault current, ensuring that the overcurrent protective device trips quickly in the event of a fault. The NEC requires that all metal enclosures containing grounding conductors be bonded to the grounding system. This ensures that any fault current on the grounding conductor has a direct path to ground. In addition to providing a fault current path, the ground wire inside the conduit also helps to reduce electromagnetic interference, often referred to as EMI. EMI can disrupt the operation of sensitive electronic equipment. By providing a grounded shield around the grounding conductor, the ground wire can help to reduce the amount of EMI that is radiated from the conductor. In summary, while metal conduit can often serve as an equipment grounding conductor, there are certain situations where a supplemental ground wire is required. These situations include when the conduit is not continuous, when it is not properly bonded, when it is installed in a corrosive environment, and when it is used to protect a grounding conductor. By understanding these requirements and following the guidelines in the NEC, you can ensure a safe and reliable electrical system. Consider a scenario where a bare copper grounding conductor is run through a metal conduit in an industrial environment. The conduit provides physical protection for the grounding conductor, but it is also exposed to potential mechanical damage. If a forklift accidentally strikes the conduit, it could damage the conduit and the grounding conductor inside. If the grounding conductor is damaged, it may no longer be able to effectively carry fault current. To prevent this, a ground wire is run inside the conduit along with the grounding conductor. This ground wire provides a redundant grounding path, ensuring that the electrical system remains safe even if the grounding conductor is damaged. It's also important to understand that the size of the ground wire is determined by the rating of the overcurrent protection device protecting the circuit, as referenced in NEC Table 250.122. Always consult the latest edition of the NEC and local electrical codes for specific requirements in your area. Moreover, it's crucial to remember that relying solely on the metal conduit as the grounding conductor without proper bonding and continuity checks can be a dangerous practice. Over time, connections can loosen, corrosion can occur, and the effectiveness of the conduit as a grounding path can diminish. Regular inspections and maintenance are essential to ensure that the grounding system remains in good working order. If you're unsure about any aspect of grounding or wiring, always consult with a qualified electrician. They have the knowledge and experience to ensure that your electrical system is safe and compliant with all applicable codes and regulations. Electrical safety is paramount, and it's always better to err on the side of caution when dealing with electricity. By following these guidelines and seeking professional advice when needed, you can minimize the risk of electrical shock, fire, and other hazards. Proper grounding is a fundamental aspect of electrical safety, and it's essential to understand the principles and practices involved in ensuring a safe and reliable electrical system. Ignoring these principles can have serious consequences, so it's always best to prioritize safety and seek expert guidance when necessary. Furthermore, it is always a good idea to consult with a qualified electrician on projects with high electrical demands like electric vehicle charging stations, welding circuits, or other similar large capacity loads to ensure that it is properly grounded for safety and reliability purposes. Electrical codes continue to evolve over time, and it's important to stay up to date on the latest electrical safety practices.